All right, welcome to your profile analysis video lecture. Profile analysis is when you go on Facebook and you analyze somebody's profile. No, that's not right. Profile analysis is where you ask your friend to turn to the side and then you analyze the side of their face. No, that's not right either. Okay, sorry, this is serious business. Profile analysis is a special case of multivariate ANOVA. And it's a situation where there is more than one DV, as in MANOVA, but unlike, or I guess in a special case of MANOVA, the dependent variables are all measured on the same scale, which should remind you of a repeated measures study. So this could be a repeated measures study on the DV. It could either be one DV measured more than once, as in repeated measures, or it could be more than one DV all measured at once, as in like dependent samples. So either way, it's MANOVA, but it's a special case. And the most common application of such an analysis is when subjects are measured repeatedly, so it's repeated measures and a multivariate approach to studying repeated measures. So when would you use it? Well, as we go through the video, I want you to sort of think critically about when we're sort of going back and forth between having a variable as an IV and a variable as a DV, because really we want to make sure that we are representing our hypothesis properly. That is our number one goal if we're using the scientific method and selecting the appropriate statistical method to accompany our hypothesis. So in mixed ANOVA, we're declaring a variable as an IV. In profile analysis, we're kind of like switching that IV to a DV, and we just have to be really careful when we use each one, and be very careful that our selection matches our hypothesis. So that's the sort of the bottom line here. Statistically, we use profile analysis when we have enough of a sample size. That is, if you have more subjects in your smallest group than dependent variables in your design. So if you don't have enough subjects in your smallest group for comparison, suppose like, as we're going to see here, we're comparing non-depressed and depressed folks. So suppose we only have a couple of people in our depressed group. Well, then we shouldn't be expanding our design out, certainly. And then to include, let's say, another DV. And then also when your data violates the assumption of sphericity, so you may have heard of and even studied sphericity in the past. It has nothing to do with spheres. It has to do with correlations between pairs of levels of your independent variable. So you may have seen this definition before. The idea with sphericity is it underlies repeated measures or dependent samples designs. So if samples are dependent on each other, then they are going to be correlated with one another, and in particular at pairs of them. So for example, if you have 3 time points in a repeated measures design, time 1 and time 2 should be correlated. Time 1 and then time 2 should be correlated with time 3, and those correlations should be roughly equal to each other. If they're not, then it implies, let's say, time 2 and time 3 are not actually dependent on each other. If their correlation, say, is much lower than the correlation was between time 1 and time 2. So if there's no dependence there, then it calls into question whether you should be doing a dependent sample study. So hopefully that makes sense. And if it doesn't, then you can feel free to rewind me. But I'm trusting that you've at least seen this concept before. And so going back one slide here, if our data violates the assumption of sphericity, then we're using profile analysis, meaning that so this is the sphericity test that is printed in SPSS. It is named after John Mauchly, who you may or may not have, first of all, known that his name is pronounced Mauchly, and second of all, he designed the first ever computer, and his name is more synonymous with tests of sphericity than computers these days. But anyway, if this test is run and it's not significant, then we're okay to do our ANOVA. This is the assumption of sphericity. So let's say our data violates this assumption. Then we run profile analysis. And again, this is sort of the statistician talking about when you should run profile analysis. The psychologist would say, hold on, like, why are we letting sphericity assumptions guide our choice of method? Why don't we go back to our hypothesis and make sure our IVs and our DVs are lined up correctly? That's probably more the theoretical basis for profile analysis. But the statistician will be like, well, let's check sphericity, or we just enjoy MANOVA. I like running those matrix multiplications and finding lambdas and determinants and stuff. Let's do that. Okay, so let's do that. So suppose a non-depressed group and a depressed group are compared here, and this is going to be the foundation of our study. I took another, or our example, I took another Tabachnik and Fidel example and altered it a little bit so that it's a little bit more like actual research that one or more of you might do. Comparing non-depressed and depressed groups on these, I thought made sense because, maybe folks in a depressed group or someone who's experiencing depression may be less likely to, let's say, participate in leisure activities. And these leisure activities, reading, dancing, and watching TV, are collectively the DV. They are grouped into a leisure activity category, but you can imagine that there might be differences within those leisure activities. For example, someone who is, let's say, in the depressed group may be less likely to dance than someone in the non-depressed group, we could say. So we start with a leisure activity hypothesis, and then we break it down within the DVs, and we can look at those as a follow-up or as part of our profile analysis here. So here's your data, a very small sample size. I'm going to show you how this plays out in SPSS here in a minute. You've got 4 people, and they each rate on a scale of 1 to 7 how often they participate in these activities, thereby putting the DV on the same scale. That is, reading rating is 1 to 7, dancing rating 1 to 7. They're all on the same scale, and so that implies we can do profile analysis rather than MANOVA. There are, just like in two-way ANOVAs and MANOVAs, just like in those designs, there are 3 hypotheses that we make. They're a little bit different, though, in the end. So you'll not see main effect 1, main effect 2 interaction. Instead, you'll see the following. So the first hypothesis here is a difference between groups. This looks like a between subjects or independent samples ANOVA main effect. And in this case, we're making a hypothesis clumping all leisure activities in together and hypothesizing that the 2 groups are different. So this is called the levels hypothesis because you're comparing the different levels of the IV. In this case, there are 2 levels, depressed and non-depressed groups. Then we make a second hypothesis about our DVs being different than each other. So if this were, I'm sort of carrying this through as a comparison to two-way mixed ANOVA. This would be a within subjects main effect in two-way mixed ANOVA. It would be the dependent samples main effect, let's say, and that is reading, dancing, and watching TV are different in popularity, but in a mixed ANOVA, they would be treated as an IV. Here, we're treating them as a DV, and so, again, we have to think about what our hypothesis might have been to begin with. And so if our hypothesis is that is not something specific to these activities, but rather centered on the differences between depressed and non-depressed groups on collectively leisure activities, then that implies more of a profile analysis. So it's a little bit of a subtle difference here, but you can think about that, as I mentioned, as we continue on and see if maybe profile analysis is preferred versus mixed ANOVA in these examples or not. So anyway, this is your second profile analysis hypothesis. It's called the Flatness Hypothesis. Why is it called the Flatness Hypothesis? Well, you're testing to see if there is a difference in the DVs, or no, trying to reject a null hypothesis of no difference between the means of these DVs. And if there is no difference, then if you were to draw this out on a graph, which is done sometimes for profile analysis, then the slope of the line is flat. So you would see like a horizontal line here if there were no differences on reading, dancing, and watching TV, implying that the x-axis would be the 3 categories and the y-axis would be rating, something like that. If there is a difference, that line would not be flat. All right, that was number 2. And number 3 is kind of like the interaction, but it's now, well, what is it? It's the non-depressed group and a different pattern for them or profile existing for the non-depressed group as opposed to the depressed group. So the profile, the term profile here, is that the non-depressed group has a different profile of leisure activity. They like to dance more than they like to read or watch TV, but the same is not true for the depressed group. The depressed group maybe does not like to dance so much, or maybe they like to watch TV more, something like that. So there are different profiles for the two groups here, and that's our parallelism hypothesis, and it might remind you of when you are testing for an interaction. You might look for parallel lines on a graph, right? So we're going to look for parallel lines on a profile if we choose to graph this. And ultimately, we'll get a p-value to let us know if the first group is parallel to that of the second group, or if the profiles are similar. So in the book example, I replaced, what did I replace? I replaced administrators and politicians with depressed, non-depressed, and then I eliminated the belly dancer category. So our example actually is the same example as the book, but just simplified here, Tabachnik and Fidel, page 320. This is our profile analysis graph that we will get a simplified version of this, or I guess a subset of this in a minute in SPSS. So you can see that the profiles are graphed here, and the middle one there is the belly dancer group, and they're sort of in between. They like everything equally, and then the administrators seem to dislike everything, and the politician's the one in the middle. That's right. Politician's one in the middle. The belly dancers are the ones that seem to like everything, scoring highly, especially on dancing, of course. And then the administrators, like I mentioned before, are the ones that don't like anything and are low down there. So we can look to see if these lines are parallel. There will be a p-value that will be associated with that, and we can also look at some of the other characteristics of these three groups. In our case, just two groups, depressed and non-depressed, and just 3 leisure activities as opposed to 4. So simplifying it down. All right. Time to do some calculations. For the first hypothesis, we're going to combine our DVs together. Why do we do that? Well, we're just looking at leisure activities. So we're not interested in the differences between reading, dancing, watching TV. We're just combining them together. And literally what we do is we just take our 3 scores per person and average them and feed them into an independent samples ANOVA. So if we want to look around on this one, I'm going to rewind you back to an earlier slide, and we can compare here. So this is your data. So that first person in the profile analysis here, it's a scoring of 4 right here. The first person in the non-depressed group is 4, and if we go back to the raw data, that person here is 4, 4, and 4, reading, dancing, watching TV. So the average of those 3 is going to be 4. And then for the next person scored 6, 4, and 5, so we might expect an average of 5 to show up in the graph, or in the chart here, and here's that 5. Right? In the depressed group, the first person is a 1.67 on the mean. That is combined here, and it is the average of 3, 1, and 1 for that first person. So we take a bunch of averages. I did that sort of privately and then fed them into the slide here. And then ran you through a sum of squares between and sum of squares within, and just asked you to follow through an independent samples ANOVA. So I'm going to fly through that since we've seen that before. Again, you combine your DVs together by averaging, in this case, the 3 values on each for each person, and then you run the independent samples ANOVA. You're going to get your sum of squares between, your sum of squares within, your F statistics, everything's standard here. So in this case, you're going to get an F of 17.16. The critical value is lesser, and so we're going to reject our null hypothesis and conclude a difference between depressed and non-depressed folks. And so then we move on to the next hypothesis. P-value 0.003, we'll see that here in a minute in SPSS. Hypothesis 2 is bringing reading, dancing, watching TV back into focus here. This is the flatness hypothesis. So what we need to do here is, it might remind you of a dependent samples t-test, because in a dependent samples t-test you may have learned to take different scores to then set up your calculations. So in this case, we're taking different scores for the non-depressed group, reading minus dancing, and then you're taking the same thing for the depressed group, reading minus dancing. You're getting an average difference score for each group, and then you're getting a difference score grand mean, and what that is just the mean of, let's see, 5 people, 10 people, right? 5 in the non-depressed group, 5 in the depressed group, and you're taking the mean of those 10 difference score values. So in this case, 0, 2, 0, 0, negative 1, and on non-depressed, and 2, 2, 2, 6, 3 for the depressed group. The grand mean of all those 10 values is going to be 1.6 here. And then so that was dancing and what was it? Reading and dancing. Now we're doing dancing and watching TV. Same process, different scores for each one, for each group. And the difference score grand mean is the mean of those 10 differences that you see there. So I gave you reading and dancing. I gave you dancing and watching TV. I did not give you, what was missing there? Reading and watching TV, which in this case you could do but would be redundant. Or not necessary for the calculation. So you just need to do 2 of the 3 combinations of difference scores to set up your sums of squares for the difference scores. So this is what you need. You knew the matrices were coming eventually, so here they are. In the previous video for MANOVA, I tried to dictate a little bit where these difference scores came from. Flipping back and forth between slides. I'll try to do that again here briefly, but then it may be best for learning if you just meet with me or we go through it in class on the board, because the flipping back and the dictating on the video is not necessarily the most instructive. But I'm going to give it a shot here. So 0 minus 0.2. So where did that come from? Well, this is a difference score sum of squares. So we're using the difference scores. That is our data. And so that 0 minus 0.2, that is for the first person. And so we're going to look back at the first set of difference scores here. The 0 for that first person is the difference score on reading minus dancing, and because it's 4 minus 4, right? And then the 0.2 comes from the group mean for the non-depressed group on the reading minus dancing comparison. So that gets plugged into sum of squares within. Then we have below that 0 plus 0.4. So that is the same person here, but on the second comparison group. So you're going 0 here for the first person, minus negative 0.4, right? So minus negative becomes positive. So this is still the non-depressed group. The first person, the same person, gets put in this vector here. And then this process should look familiar if you have already gone through MANOVA, because we're taking a matrix and turning it on its side as a transpose, thereby multiplying these deviations by each other. This is one term for each of the 10 people. So the dot, dot, dot implies 10 people. Okay, so I'm going to talk about the 10th person here in the list. This is the last one here. The 3 minus 3.0 comes from the 10th person, which is the last person in the depressed group. Sounds very sad. I'm the last person in the depressed group. That's not who you want to be. But anyway, they scored a 3 here on the difference score of reading minus dancing, 6 minus 3. And then minus 3.0 is the mean for that particular group. That's the depressed group on the reading dancing difference. So that's where the 3 minus 3.0 comes from. Then we go to the next difference score list here. The 0 minus 0.2 comes from that same person. Here's the 0. And then the 0.2 comes from the depressed group on that particular comparison dancing and watching TV. So you just need to follow it through. It's going to be one unique term for each of the 10 people. Like I said, if you're trying to trace this along and the video doesn't do it for you, let me know. We can meet in person and also go over it during class. So after all of the exciting calculations, we have a sum of squares within statement here. This is a sum of squares on the top left, another sum of squares on the bottom right, and then some cross products on the diagonal top right and bottom left. And if you're unclear about the process, the multiplying of the matrices and the addition of the matrices, you can review the MANOVA video, or you can again just come talk to me. We can run through it. So we've got a sum of squares within. Well, where are we going with this? Well, we need to eventually get to an F statistic, again, to evaluate our profile analysis hypothesis. So that's where we're headed. But first, we need to take an inverse of a matrix. This is even more exciting. Here is a super quick introduction to what an inverse of a matrix looks like. So if you're taking an inverse of a number, it's just 1 divided by that number. But now we have a matrix, and so you see like a 2-row, 2-column matrix here. If you're taking the inverse of it, you are shuffling the elements around. So you switch A and D, top left and bottom right, in location. You keep C and B where they are, but you make them negative. And then you put out in front 1 divided by the determinant of the matrix. And the determinant we also saw for the first time in the MANOVA video. And that determinant is just a number. So that 1 over that number out in front is just going to be a number that you multiply each element of the matrix by in turn. So for our particular example here, we take our sum of squares within, and this is what the inverse looks like. You're going to switch your 6 and your 16.8. You switch your 5.6 and 5.6, but they're the same as each other. Actually, no, you don't switch them. You keep them where they are. You just take the negative instead of the positive, right? Because you're keeping C and B where they are and just taking the negatives of each. So the negatives of 5.6 negative becomes 5.6 positive. And then out in front there we see the determinant. The determinant is the top left of the original matrix multiplied by the bottom right, 16.8 times 6 minus negative 5.6 squared. Whew. And you get your sum of squares within inverse, which has some decimal numbers there. Looks pretty small. What do we do with this? Well, we need to go back and consult with Dr. Harold Hotelling from the University of North Carolina. He was a star basketball player for the team. No, I just made that up, actually. He was a professor of statistics at North Carolina. I got him confused with Michael Jordan for a minute. Anyway, on to the next thing. Hotelling's t-squared. You will see this showing up in SPSS, only SPSS calls it Hotelling's trace. I don't know, same thing. I think different books have it labeled as different ways, but either way, it belongs to Hotelling, the statistic. And it is similar to Wilks lambda. It's another, in fact, we could have calculated a Hotelling's t-squared for our MANOVA. And for whatever reason, it's more popular to have Hotelling's t-squared as the mechanism by which we get from our sums of squares and matrices to the conversion to an F value. For whatever reason, this is preferred for profile analysis as opposed to the Wilks lambda, which is preferred for MANOVA. I don't know. That's something you guys could look up as to why this is preferred, but it will get us to our decision. So here is your t-squared, your Hotelling's t-squared formula. That inverse that we just took is the middle term, so that 0.086, 0.081, that matrix came from a couple slides ago when we took the inverse of the sum of squares within. Then we're taking the capital N out there is how many people we have in our study. So we have 2 groups of 5, total of 10 people. And then the grand means 1.6 and negative 0.1. Where does this come from? So let's go back a couple of slides to show you where these values came from. You knew I printed these on the slides for a reason. Okay, there they are. This is the difference score grand mean number 1, 1.6, and the difference score grand mean number 2, negative 0.1. So those get plugged into our t-squared formula. And we're multiplying a 2-column by 1-row matrix by a 2 by 2, 2-row, 2-column, and then multiplying that by a 2-row by 1-column matrix, and we have the 10 out in front. You can't forget about that. So if you're curious about the details of multiplying these matrices together, what happens is basically you're going to take a 1. So when you have 2 columns there and 1 row in the first matrix, you multiply that first by the 2 by 2 matrix, and you're going to get what? You're going to get a 1 row by 2 columns, so it's going to end up being a 1 row by 2 column matrix. And then you multiply the 1 row by 2 column matrix by a 2 row by 1 column matrix, and you get a number. So it all reduces down to one number magically, which is a 1 row by 1 column matrix in the end. So again, we can go over in class the rules for these multiplications, but I'm going to continue on here. So through this matrix multiplication, we get a number that represents those 3 matrices, and then we multiply that number, or I guess you could multiply the 10 first. Either way, the 10 should be accounted for and not forgotten. So I guess my recommendation here is to multiply that first matrix by 10 first. In this case, you would get 16 and negative 1 once you multiply 10 by that first matrix, and then probably just go in order. That's probably the easiest thing, so you don't forget about the 10. Then you multiply that matrix by the middle one, and then you multiply the resulting matrix there by the last one. And so you go in order of operations there. So ultimately you get 1.978. Time to convert this to an f through this mysterious formula. You take your t squared and you put it out on the right side there. Your n is 10, total number of people. K is number of groups. In this case, we had 2 groups, depressed and non-depressed. P, number of dependent variables, which was 3. That's what it looks like. And so you're going to get your f, 6.92. Your degrees of freedom here are p minus 1. What was p? P was number of dVs. That's annoying because you might confuse your number of dVs with your p-value. Call it something other than p. Come on, Harold Hotelling. Oh well. Anyway, p minus 1 in this case, 3 dVs. Minus 1 is 2. Degrees of freedom. The second value is this n minus k minus p plus 2, which comes out to be 7. Again, 10 is your total number of people for n. K is the number of groups for your IV, which is 2. All right, so this is your conversion here. Your f value, 6.92, is going to be greater than your critical value in this case. And so we're rejecting our null hypothesis. Again, we can see this 0.022 in our SPSS here at the end of the video. All right, all of that, and that was just our second hypothesis. People worked hard on this profile analysis stuff before computers. Ooh, Harold Hotelling was doing this before SPSS existed. Wow, okay. Now, for hypothesis number 3. So hypothesis number 3 is sort of the interaction type of looking hypothesis. We're looking at if there is a different profile for the non-depressed group as compared to the depressed group. This was the parallelism hypothesis in profile analysis terms. And luckily for this one, we've already done some work, so I recommend doing it in this order as opposed to trying to flip it around. So this may look familiar. This is your Wilks lambda, and your Wilks lambda is, again, it's just a mechanism to get you to an F statistic here. The books recommend Hotelling's t-squared for that second hypothesis, and Wilks lambda for this, the parallelism third hypothesis. Theoretically, we could do Wilks lambda the whole time and maybe get the same thing, or do Hotelling's t-squared the whole time and maybe get the same thing. So if you're at all interested in these methods and the reasons behind the madness, let me know and we can debate those things, look up some literature. Fun stuff. All right, so we've got our sum of squares within here, which we've calculated before, but when we were doing the second hypothesis, we took the inverse. Here we don't, we just keep it as a sum of squares within. Now we need our sum of squares between. And so again, I'm going to try to match these numbers up to what we need. The sum of squares between calculation is going to be the same as what we did for MANOVA, except just a different application here. So we got to find these numbers. So the 0.2 and the 1.6, I'm scrolling back. The 0.2 and the 1.6 come from these different scores. So the 0.2 is the group mean for the non-depressed group on reading minus dancing. The grand mean here, 1.6, is what you're subtracting. So this is a sum of squares between, right? So we're looking at group mean minus grand mean, and so that's what this is. The non-depressed group on the reading dancing comparison, 0.2 is the mean, and the difference score grand mean for reading minus dancing is 1.6. So what that is implying is that the non-depressed group is not showing much of a difference, right? 0.2 on reading and dancing, and then we see that the depressed group is showing a pretty big difference, 3.0, in that they seem to prefer reading over dancing. All right, so let's go back to our sum of squares between. So the 0.2 minus 1.6 appears in your sum of squares between calculation in the top of the vector. The bottom of the vector here, negative 0.4 plus 0.1. We're going to go back to negative 0.4. That is the non-depressed group on the second comparison here, dancing minus watching TV. Subtracting negative 0.1, so that's a plus 0.1, right? Minus a negative. So those go in for your first term here, and then since it's a sum of squares between, we're going to repeat this 4 times. So you're going to just have that multiplication there and put a 4 out in front. For the second one here, we've got a 3.0 minus 1.6, so we can scroll back to see where that comes from. That's going to be the depressed group. 3.0 here, difference score, 1.6 grand mean. And so you might start to see the pattern now, especially if you've done this already for a MANOVA. The second one here, 0.2 plus 0.1, comes from 0.2, depressed group, second difference score, dancing minus watching TV, depressed group mean, 0.2, and then the negative 0.1 grand mean, again, gets subtracted and appears here as a plus 0.1. Okay, so this one term there's one term for each of the 10 people. I think I said you do it 4 times you do it 5 times because there's 5 people in each group. So you're going to do this 5 times for the first group and 5 times for the second group. So you can just put a 5 out in front, as is shown here, for each term, and you're going to multiply them through, and you're going to get the matrix seen there. So we're going to fill out our Wilks lambda by plugging in our sum of squares between. Again, the sum of squares within came from the previous hypothesis, so we're not repeating that work unless we really want to. And then we add on the bottom, and then we take determinants. So these are determinants again as introduced in the MANOVA lesson. The determinant of a matrix is the top left multiplied by the bottom right minus the top right multiplied by the bottom left. And that's true for a 2 by 2 matrix, 2 rows, 2 columns. So it gives you one number. In this case, it gives you one number on the top and one number on the bottom of the fraction. And we're going to end up with 0.28. And we're almost there. As in MANOVA, we got to convert that Wilks lambda to an F via the same formula with the y's and the degrees of freedom in there. So this is, again, like we did with MANOVA. I will go ahead and make this slightly bigger. We're going to get 0.28. That's our lambda. We're going to do 1 over S in the exponent. The S is the number of different score combinations in this case. That's the only change from the instructions for MANOVA. You're just using different scores now. So what does that mean? Well, we have 2 different score combinations, right? That we used. We ignored the third combination and just used 2. But either way, that's the greater of the 2 values here. The lesser of the 2 values is degrees of freedom between, which is number of groups minus 1, which is 1 in this case because there are 2 groups, just the depressed and the non-depressed group. So the 1 goes in the exponent there. Moving forward, 0.28 stays the same. Then we have a number of different scores here as plugged in. Instead of for MANOVA, it was number of DVs. So you just got to remember number of different scores is what we use when we're doing this parallelism hypothesis. So in our case, we had 2 different score combinations again. So that gets put out there or put up there in the formula as 2. So our degrees of freedom 1 is 2 multiplied by 1. Our degrees of freedom, the second value there is degrees of freedom within, 8. That is your 10 total people minus 2 groups. 10 minus 2 gives you that 8. The degrees of freedom between was 1, as we mentioned. So this comes out to 7. So we've got 2 and 7 for our degrees of freedom. We plug those into the formula like so. The y value is the Wilks lambda to the first power, or just Wilks lambda back again. This gives you 9.06. If you're trying to do this just based on this slide, I think I round 0.28 in this slide. I think it's like 9.0 instead of 9.06 or something like that. But if you keep more decimals in that 0.28 as you go along, you're going to get 9.06 more precisely. And that 9.06 is greater than the critical value. We reject our null hypothesis. We have a 0.011 p-value, which will appear in SPSS shortly. Okay, so I have set up our profile analysis here in SPSS to be run. I have labeled our depressed and non-depressed groups as 1 and 2. And then I've also included a case number here just to keep our people straight, because we need to remember that we have 10 people here, so that's just a reminder. Reading, dancing, and watching TV are our 3 dependent variables. We don't need to calculate those difference scores. We don't actually need to do anything other than run through our profile analysis in one step. So SPSS is really doing a lot of work for us. Well, SPSS always does a lot of work for us, but especially in this case. So we're just going to run through it. We've got, it's a similar setup for, let's say, an independent samples ANOVA, by the way, except now we have 2 additional dependent variables here. All right, so we're going to go to Analyze, general linear model, and repeated measures. So there is no profile analysis option within the multivariate ANOVA section, even though this is a multivariate ANOVA. For whatever reason, we have to run it through repeated measures. So I'm going to call factor 1 leisure activity, or just let's say leisure, which I just misspelled. Okay, with 3 levels, right? There's 3 different types of leisure activities here. Click add, click define, and we're treating this as a within subjects or repeated measures IV, which it isn't. So we're kind of just talking SPSS into getting us what we need, even though it's not technically running a profile analysis. It's still going to run the statistics that compose a profile analysis, and so we'll get what we need. So it's kind of backwards here a little bit in SPSS terms, but we will land on the right statistics. All right, so we put leisure activities, reading, dancing, watching TV over and within subjects variables, and we're going to remember that it's a DV when we interpret, and then we're going to put group over to between subjects factors. I've got 3 more variables in here, which you will see a little bit later as part of our next example. But meanwhile, this is what we need, and this is really all you need to do for your homework. I'm going to give you a plot, though, just to show you a little bit more of what profile analysis looks like. So I'm going to put leisure over on horizontal axis and group over on separate lines. This is going to give us a graph that looks a little bit like an interaction graph, and will allow us to compare the profiles graphically of our 2 groups, that is, the depressed group and our non-depressed group. So I'm going to click continue, click OK. Again, you don't need to get the plot in your homework, just the statistics. And here we go. Okay, so what do we need? Well, let's go back to our notes here and flip back and forth. The first result was just that ANOVA result, right? So the first hypothesis was evaluated like so. All right, so this was our first hypothesis. The non-depressed and depressed groups are different. The result in our notes here was an F value of 17.16. Which allowed us to reject that null hypothesis. So where does that 17.16 show up? It shows up in our tests of between subjects effects. So it's a little bit hidden away here, but this is a between subjects effect. So that should guide where you're looking for it here. 17.16 is hidden here. The 0.003 p-value corresponds, and the 32.03 and 1.87 also show up as sum of squares values, or I should say mean square values. In your output. Okay, so that was the first hypothesis. The second one was the flatness hypothesis. Reading, dancing, and watching TV differ in popularity. This is when we started calculating difference scores. We had our F statistic here, 6.92, so that one shows up back up here in the multivariate test box. So we've got our 6.92 here as our converted F. Remember, we used a Hotelling's T to get there. The Hotelling's T was 1.978. I mentioned just a minute ago that the Hotelling's T shows up in SPSS as Hotelling's trace. Same thing, 1.978 there. Degrees of freedom 2 and 7, p-value 0.022. So there's your hypothesis number 2 assessment by SPSS. So for the third hypothesis, we're remember, this is the parallelism hypothesis, looking at whether the non-depressed group has a different profile than the depressed group. So for this one, we ran through the Wilks lambda calculation. We got a 9.06 for our F. This 9.06 appears in the same multivariate test box, just right below the previous F value. So this one is 9.06 here. The Wilks lambda there, 0.279. In our notes, that was 0.28. The p-value 0.001. So that's where you can grab your SPSS output, and it may look a little bit like a mixed ANOVA when you're running it through SPSS. Like I mentioned, you kind of have to fool SPSS into giving you these statistics, but it does, and the multivariate test box is the place to find them. So I guess what SPSS is doing is running a mixed ANOVA and also a profile analysis and letting you pick the right one. Man, is it doing a lot of work. All right, so moving back to the notes to introduce the doubly multivariate design, and then I'll just show you SPSS for this one. I'm not going to show you the calculations. So a doubly multivariate design and a two-way repeated measures or mixed ANOVA, no, not ANOVA, MANOVA are often used to answer similar research questions. So the two-way MANOVA that we ran through last time, or in the last video, is the comparison here. Do we use a doubly multivariate or do we use a two-way MANOVA? Well, let's see what the application of it is. If one of the repeated measures IVs in your two-way MANOVA, okay, so if you have an IV in your two-way MANOVA, that violates the assumption of sphericity, meaning that we need to assume that at least one of the pairs of levels in your design, in your repeated measures IV, is uncorrelated or different than the other pairs. Then you should probably switch it to a DV and do a doubly multivariate analysis. So it's an interesting set of circumstances. I think ultimately, again, what do we do as psychologists? We compare to our hypothesis, right? We compare, does this variable make sense as an IV or does this variable make sense as a DV? And we go with it that way as opposed to trying to let assumptions of sphericity guide us theoretically. But assumptions of sphericity are good to check up front in real life, especially when you have a big enough data set to be able to judge Mockley's test and so on. All right, so here's an example. We can derive perhaps more knowledge of when to apply such a method from the example. So we have our depressed and non-depressed groups, and suppose they're asked how much they enjoy each activity, but also how many hours per week they take part in each activity. So we're just adding a new wrinkle or an additional wrinkle, and that is, instead of just enjoyment of the activity, we might say, well, it's one thing to enjoy an activity, but if you never do it, it's not really a very good measure of, let's say, suppose we want to assist someone with depression, symptoms of depression. So we're like, all right, studies show that dancing is a feature of those who are not depressed. So maybe we encourage somebody to dance if they show that they enjoy it. Well, it's one thing to enjoy it, but it's another thing to actually do it. And so then the number of hours per week is added in here as an additional DV. So this is, we're getting more and more data based on our 10-person sample here, 5 in each group. So for example, that first person in the non-depressed group rated reading as a 4 out of 7 on the enjoyment scale, and they read, let's say, for some minimum amount of time, twice per week. For dancing, they rated it again as a 4, and they do it once a week. For watching TV, they rated it as a 4, again, but they do it 14 hours per week. It depends on our scale, I suppose, for watching TV in these per week measurements. But we're going to go with hours, so this non-depressed group is watching a lot of television, it appears. The depressed group is doing a lot of reading, it appears, and not a lot of dancing. So we'll go with this as our added wrinkle here. Not only is it how much you enjoy an activity, it's how much you actually take part in the activity. And so I'm just calling this enjoy/take part. So these are repeats of the hypotheses with that as your added measure. So I think you can kind of see that, like, well, maybe there's an additional way to measure this thing, this dependent variable of participation or appreciation of leisure activities, we could call it. And so if there are multiple ways of measuring that, then we add in another multiple measure or doubly multivariate design. Okay, so hypothesis 1 is the same as before. There's a difference between the depressed and non-depressed groups in this leisure activity stuff, and in this case we're just saying enjoy/take part as opposed to just enjoy. Here we're saying reading, dancing, and watching TV for the second hypothesis are different across both groups in enjoyment/participation, and then the third one, the non-depressed group, enjoys dancing or takes part in dancing more than reading and watching TV. And you can see here also that this lends itself to a follow-up profile analysis, because maybe you can't see that, but since we were using enjoyment before, now we add in taking part as another DV, a related DV. We run those together, we get a significant result, let's say, for one or more of our hypotheses. Then we follow up with profile analyses, and so in this case you would follow up with an enjoyment profile analysis and a taking part profile analysis, which is pretty much awesome. Okay, so let's do the math. No, let's not do the math. I'm going to switch over to SPSS and we will conclude the video from there. All right, so for SPSS, for the doubly multivariate design, I have added in 3 additional columns here. This is the read per week, dance per week, and TV per week columns coming from your data. And so we are ready to run this. So we're going to go back to where we went before. Again, this is like, you're going to run this, and then if you get a significant result, you would follow up with a post-hoc profile, a pair of post-hoc profile analyses. And one of which, in this case, we've already run because we already ran the read, dance, watch TV profile analysis for enjoyment. We didn't. The other part is new, however. So, okay, so to run this analysis, we're going to go to Analyze, General Linear Model, and Repeated Measures. And this time we're going to declare 2 factors. I'm going to clear it here, and we're going to start from the beginning. I'm going to put in interest first. This is I'm calling it interest because it's the 2 levels, and the 2 levels are like enjoyment and per week. So maybe you could say collectively that it's how much someone is interested in this particular leisure activity. So I'm going to put that in first, and then I'm going to put in the type of activity, or just call it leisure, second. Again, I spelled it wrong. And then I spelled it wrong again. Okay, leisure, there it is, with 3 levels, and I'm going to put that in second. If you follow that sequence, it's going to be a little bit easier to do the 2-level variable first, followed by the 3-level variable in that order, because then when we go to define, we can move stuff over in order, and yeah, it should look like it's appropriate here. So we're going to go and just move all 6 of the variables over in turn, and then we just got to double check to see, as you would in a 2-way repeated measures ANOVA here, you got to just double check the labels. So read is 1-1, that is enjoyment of reading and the reading category. So 1 is enjoyment and 1 is reading. And then for dance, it's 1 is enjoyment, 2 is dance, and then 1 is enjoyment, 3 is TV as you go down the list there. For 4, 5, and 6, you have read per week, that is per week, that's the 2, and 1 is reading. Then the 2 for dancing per week, 2 is per week, and 2 is dancing, and then 2 for the last one is per week, and 3 is TV. So if you flip the order of the factors, you have to do more double checking of that order just to make sure the labels properly match up. But here we've got it organized already in order. The group variable goes into between subjects factors as before. We could also get some plots here, but I'm just going to, since this analysis already has so many layers to it, I'm going to just get you to the result. And the result is going to read similarly to what we saw for the profile analysis. So we're going to start with hypothesis 1. Hypothesis 1 was the let me show you hypothesis 1. That is this one here. The non-depressed and depressed groups are different in how much they enjoy / take part in leisure activities. This is the levels hypothesis. And really you're combining everything together just to compare depressed and non-depressed groups. So we're going to go down to test the between subjects effects, and we're going to compare here the F statistic that ultimately results here is 1.349, p-value 0.279. So we're actually finding that there is no significant difference between non-depressed and depressed groups. Okay, so that's the first one. The second one is reading, dancing, and watching TV are different. So we're going to go back up, as we did for profile analysis, we're going to go back up to the multivariate test box, and we're just going to look at the first section here. This is labeled interest. So this is if there's a difference between enjoyment and participation, then it will show up in the interest section here. If we were to do the math, which we're not, but if we were, we would get a Hoteling's trace. That is 1.067. The F value here is 8.54, and the p-value 0.019. So it does appear that we have a difference between enjoyment and participation. So maybe we speculate that people are saying that they enjoy one of the activities or one or more of the activities, but not actually participating, something like that. So we could follow up. We would follow up. In real life, you would skip the follow-up for that first hypothesis, right? Because the null hypothesis was not rejected. But now that null hypothesis is rejected, and so you would follow up with a profile analysis. In your homework, I'm asking you to follow up regardless, just for practice with those follow-up profile analyses. Okay, so yeah, so then technically here you would by the rejection of the null hypothesis for hypothesis 2, you would follow up with 2 profile analyses, one for enjoyment and one for participation, and you would make a conclusion about each and maybe narrow down that, okay, reading and dancing and watching TV are different for enjoyment, let's say, but not for participation, or vice versa. All right, let's look at hypothesis 3. Hypothesis 3 is the parallelism hypothesis. There's a lot of layers to this one. It's a very cool hypothesis. The non-depressed group takes part in dancing or enjoys dancing, one or the other, more than reading and watching TV, but the same profile is not there for the depressed group. All right, so this one you just go down to the second section of the same multivariate box, interest star group. If we were to have done the math, we would have done a Wilks lambda for this one, 0.894, resulting in an F, converted F of 0.949 and a p-value 0.359. So this one this null hypothesis is not rejected, and we're not concluding a difference here. So again, in real life, you would follow up on hypothesis 2 with post hoc profile analyses, but in your homework, I'm asking you to follow up regardless. And that's it. That's your doubly multivariate design. It is awesome, and I will leave it at that.